So I run my script, and here's what I see. First of all, I filled my collection sequentially in two different ways. One was with count plus 1, and one was with row count. And as you can see in both cases, the last and the count are the same. There are 107 rows in the employees table, so the last index used is 107, and the count is 107 as well. Then I did my primary key emulation. And in this case, notice my last value is 206. It's higher than 107. Why is that? Well, as you will almost certainly find in your own tables, when you use a sequence to generate the next value, the next primary key value, you often end up with skipped values, maybe because of deletes in your table, or because of the way that sequences are buffered, allocated and buffered. But easily, the primary key values that are in use in your table are not sequentially allocated for one or densely filled. There might be gaps. So my highest primary key value is bigger than 107, but the count is still 107. Notice I was able to do my direct access to my employee ID 138. It looked up the last name Styles. And then I filled sequentially by name, indexing by name. And when I look at the last for the employees by name, that's funny, it's not a number at all. It's Zlatki. This is the last name of the person whose name is alphabetically last in the list. So the sort order of the character set determines what is highest and lowest within your index values in a string index collection. Notice also that the number of elements in my collection is 102 rather than 107. And what this means is that my employee last names are not unique. There are in fact only 102 distinct last names. Now usually when you choose an indexing scheme for your collections, you will be aiming, hoping, requiring that your indexing scheme is unique. In other words, every value, every individual string used to do the indexing is a unique value. In this case, last name is not unique, so what it means is that I overwrote the previous values several times, 5 times. Notice Oracle doesn't give you an error. It's not going to check to see whether or not that element already exists and say, no, you've already used this, that's a violation of your primary key or anything like that. This is a programmatic data structure. If you need to make sure that they're unique, you need to write the code yourself. For example, you might say, well, how can I do that? Suppose I did need to make sure that these things were unique. I could do something like this. If employees by name dot exists, so the exists method will tell me whether or not an element already exists at this name. So I could say, if it already exists, then display duplicate value, duplicate last name. So I could display the fact that there was a problem, else, and if. Let's try this. Let's grab this one block of code. Oh, no, it's hard to run separately. Let's run it all again. I run my script. And notice, 5 different duplicates. So I can write the code to guard against duplicates and do something about it, but it's something I have to do myself. Oracle will not do it for me. And finally, I do a direct access to the employee with the last name Style. So just as I could use my primary key to quote-unquote look up the record for that employee and then get the last name, with the string index collection, I can do the same thing in reverse. So if I have the last name, I go to that location in my collection of records, indexed by last name. This is a record. This is the employee ID of that record, and there it is, 138. So hopefully it's pretty clear to you by now that you can go well beyond simply doing collections indexed by integer, filling them sequentially row by row by row. You can emulate primary keys. You can use string indexing. There's an awful lot of flexibility when you're working with associative arrays. And in fact, valid table of data types are virtually anything you can declare in a PL/SQL program as a data type you can use as a table of data type. So all the scalar types, including booleans, collections of object types of records, collections of other collections, which are nested collections, which I'll talk about in a separate lesson. What you can't do is have a table of cursor variables or a table of exceptions. So those are two, excuse the pun, exceptions to the rule. Let's take a look. So here's an example of trying to create a table of sysref cursor variables. A cursor variable is a variable that points to a data set, a set of rows and columns. And here's a table of exceptions. So I can declare something to be of type exception, but it doesn't mean that I can use it as a data type in a collection. And in fact, I cannot. When I try to run either of these two scripts, index tables of cursor variables are disallowed. Notice the old name, index tables, instead of associative arrays. And encounter the symbol exception when expecting one of the following. So in this case, it simply told you this data type is not allowed. In this case, Oracle simply said that's not acceptable from the standpoint of even the syntax of writing PL/SQL code. But for all the normal kinds of data types you're going to work with, strings, dates, numbers, booleans, other collections, records, object types, you're okay. You can create collections of those elements and manipulate them. Let's talk a little bit more about valid index values. So I've talked before about how you can index by integer or by string. So what is the actual valid values that are allowed for these index values? First of all, there is no practical limit to the number of elements you can define in an associative array. In fact, the definition at the beginning of this talk talked about an unbounded list. Well, it's unbounded from the standpoint of practicality. There actually is an upper limit to the number of elements you can define in an associative array. The index values, the integer index values that are allowed in a PL/SQL collection range from -2 to the 31st plus 1 to 2 to the 31st minus 1, which is the same range as the binary integer data type. Now, that's about 4.3 billion elements. There is no way that you're ever going to create a collection with that number of elements or even close to it. Before you get there, you will blow out the memory in your session and your program will die. So that's why, from a practical standpoint, there is no limit to the number of elements that you can define. The theoretical limit is well beyond what you will ever achieve in your code. String index values can have actually any value. So if you're defining an index by string, you can use Smith, Jones, etc., etc. There's no specific range of values that is defined, only the maximum number of elements allowed in your collection. So you can use any string you want, but you can only have up to this many different strings used in your collection. Again, you will never reach that limit in practical day-to-day work with a collection because you won't have enough memory in your session. So you can use any string value you want for indexing. Let's take a look at the AA limit script to get a better sense of this and to see some rather odd behavior from Oracle. So I've declared an associative array of dates. There's my variable based on the type. And I'm going to use a small subprogram called setDate. I take the index value and I try to assign sysdate to that location in my list of dates. If nothing went wrong, I display no problem. Otherwise, I trap the exception and display the error message, format error stack. So what I'm going to do is pass in the limits. 2 to the 31st minus 1 is the highest value allowed. 2 to the 31st should be too high. Minus 2 to the 31st plus 1 is the documented lower limit on an associative array index value. I'll try one below that, and I'll try another one below that. And then I'll try to set the value to null. I run my code, and here's what I see. Let's pull this up a bit. Okay, so try to assign a value to 2 to the 31st minus 1, no problem. Try to assign a value to 2 to the 31st, and it says numeric overflow. You're not allowed to use a value that big. Assign a value of 2 to the 31st plus 1, no problem. Now here's something curious. Assign a value to index value minus 2 to the 31st, not plus 1. This is actually officially outside the range of binary integer values, but oh, Oracle doesn't make a fuss. Only if I reduce 1 past that does it give me numeric overflow. So here's a little bit of a discrepancy between the documentation and the practical usage, or the way that the collections work. I can use minus 2 to the 31st as an index value. I would essentially avoid it if I were you, in case you ever even think about using index values like this, because this could be the kind of thing that Oracle fixes in the future. Finally, if I try to assign null, use null as an index value, Oracle raises the negative 6502, the value error exception, saying that null index table key values, so index values can never be be null, whether you index by string or by integer. A little bit more details on the valid index by types. So the index by clause defines how you index the contents of your collection and what values you can use to find the elements in your collection. You can index by binary integer or any of its subtypes, including PLS integer, var char2 with an n between 1 and 32767. You can percent type against var char2 database columns, and you can use subtypes as well. Let's take a look at the various possibilities. So all of these are valid. I can index by binary integer, by PLS integer, which is the most common way that you'll see the indexing expressed, because PLS integer is theoretically more performant, faster than binary integer. Positive and natural are variations on binary integer. Positives are 1 and above, natural is 0 and above. Hey, and there's even something called sign type, which is a subtype of binary integer. And the valid values for a sign type are -1, 0, and 1. So it's used for directional purposes. It'd be kind of strange to declare an array on that type, but it's allowed. I can index by var char2s. I can index by table.column%type if the column referenced is a var char2. I can also index by %type against other variables. And I can even declare a subtype which gives another name to an underlying base data type, and I can index by that. So all these things are allowed. What's not allowed is if I try to index by an integer column type or number column type in the database. So if I try this, well, first of all, let's compile all of this and make sure that there's no problem. So Oracle has no problem with any of that. But if I put this one in, it tells me implementation restriction, unsupported table index type. Now the reason for that is that it's true that employees, the employee ID is a data type of integer. See, it says number 6. Since there's nothing to the right of the decimal point, that means it's an integer. And even though number 6 is within the range of the binary integer, basically as far as the PL SQL compiler is concerned, this is a number data type and not a subtype of integer. And the possible range of values exceeds the binary integer range. So if you're going to do a percent type against a database column, you can only percent type against string columns for string indexing. So even though, for example, I might be indexing by my primary key, let's go back to my original example of collections of records. Here I'm saying that I'm going to index by my primary key. I can't literally write the primary key definition here as I can here for my last name. So either you would put a comment. I might say indexing by primary key to let people know that that PLS integer is the primary key. Or even better is to create a subtype. So I can say subtype, the emp primary key type is integer. And then I can say, sorry, it's PLS integer. And then I can right here say this, index by the employee primary key. So now I'm documenting in my code that the index by is the primary key. I'm hiding the fact that the actual data type is PLS integer. But at least now my table definition, my collection definition, tells you what the indexing scheme is all about. So lots of different ways to index by. Generally speaking, you'll mostly index by integer, in which case you just say index by PLS integer. Indexing by string offers lots of interesting possibilities, and I have a separate lesson just on that topic to explore it in great detail. So to draw some conclusions, associative arrays are the oldest type of collection, can be used from within a PL SQL block only, and they offer a very high degree of flexibility. You have a large range of integer index values, both positive and negative. You can choose between integer and string indexing, and again we'll explore the possibilities for string indexing in a separate lesson. And sparseness, the ability to define index values non-sequentially in your collection, allows for easy emulation of primary keys and unique indexes. And that gives us some tremendous advantages when we want to copy data, usually copying data from a database table into a collection and then finding the values in that collection very quickly without having to scan through the entire contents of the collection. Well, I hope you've enjoyed this lesson on associative arrays and now have some ideas about how you can apply it in your own code. And hopefully you'll enjoy and get as much out of the lesson on nested tables and V-arrays. Happy PL SQL coding. Greetings and welcome to the PL SQL channel, a series of video trainings on the Oracle PL SQL language. My name is Stephen Feuerstein and I'm a PL SQL developer just like you. This lesson is part of my series on programming with collections, the array-like structures of PL SQL, and the focus of this lesson is using collection methods, procedures and functions defined that can be attached to the collection to get information about it or to change its contents. Some quick reminders. If you haven't already done so, check out PL SQL Obsession at toadworld.com/SF, a portal for PL SQL developers. Lots of resources for you here, most importantly from the standpoint of the lessons. Click on the demo zip link to download a zip file containing thousands of scripts that I use in all of my trainings. Click on trainings, seminars, and presentations to access the PowerPoints behind these lessons. Make sure you're comfortable with the material covered in the previous lessons in this series. I've done an introduction on collections and then defining collection types, the data type needed to declare collection variables. Finally, a note regarding chicken and egg, what comes first? To show you the methods and how they work, I have to work with collection variables, which means I declare them, and you have not seen examples of each of the different types of collections yet. So if any of it's rough and you can't follow it, just stop and take a look at some of the other videos in the series, such as associative arrays and nested tables. But hopefully my explanations will make it clear enough. So, collection methods. The term method generally is used to describe procedures and functions that are defined in a class or an object type. And you invoke a method by attaching it using dot notation to the name of the type or class, or an instance of the class. This is different from procedural approaches in which you call a procedure or a function and you pass arguments to it. So, collection methods are procedures and functions attached to a collection variable. And what's interesting about this is it was the first introduction of object-oriented syntax in PL SQL, way back in Oracle 7.3.4. So to be clear about the difference here, a method approach versus procedural approach, let's take a look at the method versus procedure file. Here's a declaration of a variable based on a predefined collection type in the DBMS SQL package. Now the delete method, which I'm going to talk about in more detail shortly, is attached to the variable using dot notation. Procedural approach would be to call the delete procedure and pass it as an argument, the collection. So in PL SQL this is not what you do. Instead you attach the method to the variable itself and then it performs the operation on that variable collection. So that's the difference between a method approach and a procedural approach. So there are two sets of methods, those that retrieve information, those that change the contents of a collection. The count method returns the number of rows currently defined in a collection, just like select count star from a table. Exists returns true if the specified row or element is defined at the index value specified. First and last return the lowest and highest index values of the defined rows. They can actually be numbers or strings. So the lowest and highest defined index values. Next and prior move you to or return the next, the highest up, or the previous, the next lower index value that is defined in the collection. Limit tells you the maximum number of elements allowed in a V-array. So these are the different methods for retrieving information. Let's take a closer look. The count method is probably one of the most popular. It returns 0 if the collection is empty. Otherwise it returns the number of elements defined in the collection, the number of defined index values. So here's an example of calling the count method. Simply attach count with a dot notation to the variable name and it returns that integer value, 0 or higher, never negative. The only limitation with count that I can see is you cannot ask for a count of elements between a range of index values. Find all the elements defined between 100 and 1000. You don't have that possibility, at least not yet. Checking for element existence. So with collections, if you try to read or touch an element at an undefined index value, Oracle raises the no data found exception. Now I think this is a bad decision on Oracle's part. They reuse the same exception for multiple circumstances, and I strongly suggest that you don't do that. In other words, if you do a select into with no row and no data is found, then Oracle raises the no data found exception. If you try to touch a row in a collection or an element in a collection at an undefined index value, Oracle raises the same exception. If you want to avoid raising this exception, you can use the exist method to check to see if the index value is defined. So, attach the exist method to the variable with dot notation, pass it the index value you want to find out about, and if it exists, then do whatever you're going to do, like display the value at that point in the collection. Let's take a look at an example. Now we're going to spend a fair amount of time with the PL/SQL loops file, looking at various ways that you can iterate through collections. But here's an example of the use of exists. I'm going from the first defined row, we're about to take a look at these methods as well, to the last. And before I try to access that variable or the element in that collection, I'm going to ask, does it exist? Now let's take a look at another file just to demonstrate what happens if you try to touch a row that does not exist and raises the no data found. So here's an example of declaring an associative array, table of strings, indexed by integer. There's my variable based on that type, and I populate it with 4 rows of information. Now, the main thing I want to show you here is the raising of no data found, so let's not worry about all the details. You'll see that in my separate lesson on associative arrays. But what I'm going to do is ask to show the value at location 2. Notice I've defined an element at index value 1, index value 3, index value 88, and so forth, but not at index value 2. So let's actually do 2 things. I'll try to display the value at index 1 and then 2. I run my script, and notice no data found at line 14. So it looks just like a select into error, but in this case I'm trying to quote-unquote select from a collection. Same error. But if we look at the output, notice it showed me the name of the person at index position 1. So that's the thing to watch out for. You might try to touch a row that doesn't exist or an element that doesn't exist, and Oracle raises no data found. The way to get around that is to first ask, does it exist? So for example, I can say, if happy family exists at position 2, then display that name, else we'll display no name at index 2. Now when I run this code, notice I no longer get an exception. I check to see if it exists. If it exists, I would display the name. Otherwise, I would display this string.